Hello everyone, my name is Kyoung-Hee Kim. I'm a professor of architecture at UNC Charlotte. Today we will discuss resiliency in the built environment, focusing on community-wide flood resilience. Community-level flooding management is critical for urban resilience. This involves both human-made and natural systems to control flooding while ensuring safety and functionalities during and after the event. We discussed nature integrations at multiple scales as a potential solution to flood-resilient built environments. Flood resilience requires a holistic integration of floodwater management that links the building and site levels, the community, and the city levels. Architectural features for floodwater management include green roofs, permeable surface, and cisterns. They help capture stormwater at the building site, reduce runoff, and retain water. This allows individual buildings to serve as mini sponges, relieving the burden on streets and sewer systems. At the community scale, shared mitigation strategies manage the stormwater runoff after building levels hold. For example, tree trenches, roadside bioswales, and rain gardens, along with sponge streets, absorb stormwater running from neighborhoods. These strategies not only prevent localized flooding, but also add green public spaces and landscapes once water drains. Finally, broader interventions such as constructed wetlands and retention ponds control runoff for entire districts. Importantly, these water management strategies at different scales holistically connect to each other and sequentially process floodwater. Therefore, it is important to plan and implement an integrated floodwater infrastructure network across all the different levels, from the rooftop and pervious pavement to the retention pond and to constructed wetlands. About 1.81 billion people, which is about 23% of the world's population, are directly exposed to significant flood risks. Nearly 1.24 billion of those at-risk individuals live in South and East Asia alone, often concentrated in low-altitude, poorly drained neighborhoods. These numbers show that flood vulnerability is not just a remote area or rural concern. It is hitting cities and communities where floodwater infrastructure may not be well maintained. Community-level flood-resilient systems effectively bridge the gap between individual building measures and massive citywide infrastructure. Collective adaptations like rain gardens on Sponge Street, bioswales along blocks, and neighborhood retention plazas can significantly reduce flood damage locally. By working at this intermediate scale, we protect people and the built environment, a first line of defense that link building-level runoff mitigation and supports larger municipal floodworks. The slide shows a community-level flood resiliency framework centered on the resilience design approach. Using 4 resilient design approach: original state, mitigate, adapt, and recover. As we reviewed in the intro video, the community-level flood resilience encircles this concept by accompanying varying flood-resilient interventions integrated with nature systems. Original state represents the normal, stable condition of the community before disruption. Mitigate involves proactive measures to reduce flood vulnerability. At this stage, the community protects its blue-green infrastructure, such as street bioswale and waterways, from stormwater surge and pollution. Preserving these natural street sponge systems is critical, as no engineered system can match their natural ability to absorb and slow stormwater. This community-level sponge minimizes potential flood damage. Adapt is the process of accommodating flood events. Communities' permeable surfaces and sponge system delay runoff so that cities' drainage and trenches are not overwhelmed. This increased lag time slows down peak flood levels and reduces stress on rivers and infrastructure. After floodwaters drain, recover is about getting the community back to normal conditions, retaining some rainwater for reuse, and releasing excess water to underground. For example, rain gardens, rainwater barrels, or retention ponds store extended floodwater and provide a water supply after the storm. Finally, release involves gradually releasing the stored water into the ground and recharge groundwater aquifers. This resilience framework converts floodwater into a resource by replenishing groundwater and enhancing long-term water security. As a result, the community maintains its original operational state and becomes more resilient to future floods. At the community-level interventions, floodwater infrastructure installations generally fall into three types: linear, nodular, and hybrid systems. Linear systems are continuous green corridors that follow streets or pathways. These include bioswale channels along roadsides, connected sidewalk planters, and rows of tree trenches. Linear systems effectively create sponge streets by enhancing permeability and connectivity along the urban pathway. They intercept runoff as it travels, absorbing and draining water over a distance. Modular systems are distributed retention nodes that hold water in public places. Examples are pocket wetlands nestled in a community park, neighborhood retention plaza designed to store water. Each node is a localized sponge, storing excess rainwater in that spot and slowly releasing or infiltrating it. By dotting a district with such water retention nodes, the community can manage flash floods where they occur. Hybrid systems are multi-purpose spaces that combine communal spaces and ecological functions. A common example is a floodable playground with integrated drainage and underground storage. These hybrids serve daily as green amenities for residents, but during heavy rain they double as flood management infrastructure. For example, a community floodable courtyard might have bioretention swales between plots, or a basketball court could be designed to detain water and return to community uses once floodwater has receded. They deliver environmental benefits while also providing public space and community value. Planners and designers can mix such strategies in neighborhood design. Together, these typologies cover the spectrum of how floodwater can be captured along its flow paths, at collection points, and through integrated community spaces. To visualize these concepts, let's look at a few representative green infrastructure solutions on the community scale. The figure on the right shows connected systems of rain gardens, flood plazas, and the city's riverside in response to delay and store floodwater. A rain garden is a mini garden bed located in yards, parks, or curb bump outs designed to retain and absorb rainwater flowing from adjacent building areas. They are usually planted with hardy native vegetation, which is adapted to water environments. Rain gardens are effective landscape features for managing runoff at the source. Even at a street corner can retain thousands of liters of water. Retention plazas, also known as water plazas, are shown at the corners of the building parcels in this figure on the right. A public square functions as a stormwater basin during heavy rain. In dry weather, it's a usable, trafficable plaza, a playground or market space. But when a storm hits, the design allows water to collect in a low-lying section. Next, the runoff continues through subsurface infrastructure like tree trenches and interconnected channels, slowly moving toward the riverside detention zone. This green terraced land in the figure acts as the final flood buffer, and ultimately the floodwater runs into the adjacent river system. This slide shows the Benthemplein Water Square in Rotterdam, which combines recreational space with floodwater retention. It remains dry for day-to-day communal activities, but can store excess floodwater in its basins. Such retention plazas illustrate how to implement multiple-purpose community spaces for both community interaction and flood mitigation. This slide shows another example of how urban spaces can be turned into flood-resilient community spaces. While the previous slide illustrates the retain and discharge of floodwater from community areas toward the riverside detention system, the landscape features in this slide show localized strategies such as rain gardens, recharging pits, and urban farming. Native species in rain gardens facilitate the infiltration of floodwater and serve to filter out pollutants. Additionally, the recharge pits capture excess floodwater and slowly discharge it to groundwater. These landscape features use natural processes within a common community area, which enhances local flood resilience and water security while providing green infrastructure for public interactions. Collectively, these multi-functioning community elements slow down runoff, replenish groundwater, facilitate water reuse, and provide access to natural spaces for the public, all while functioning as a lively day-to-day public space. This slide shows an example of sponge streets. Sponge streets refer to streets that are retrofitted or built with a suite of green and porous features so that the entire streetscape absorbs water. A sponge street incorporates infiltration trenches or soil cells under the street, and adds street trees and bioswales along the sidewalks. All these elements work in concert to capture floodwater. The goal is that instead of funneling water into sewers and ultimately causing floods downstream, the street itself can drink up the rain. This is another example of sponge streets. Bioswale corridors are vegetated swales or shallow channels that run along streets or parking lots, serving to absorb stormwater in a linear fashion. Bioswales are planted with native water-tolerant species, which slow down runoff and filter various pollutants. Bioswale along the street edge converts a hard curb into a green gutter. This not only mitigates surface flooding, but also purifies water and enhances an ecological corridor for biodiversity. This video was supported by UNC Charlotte in collaboration with the US-ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. We appreciate your interest in resilient urban development.